Section 6.2, circles, polygons, perimeter and area. Okay, this section, I'm going to start off defining defining some things, defining some different types of shapes, and also we'll find out why circles is considered as separate from polygons, because I'm going to define what a polygon is, and you'll see why circles does not fit into that definition. Then we're going to look at one particular special case of similar shapes, in particular similar triangles, because they tend to come up a lot in real life. And then we're going to run perimeter and area calculations for a bunch of different types of shapes. So that's what this section is going to be. So let's start off with those definitions, defining each type of shape. So let's start off with circle. It's kind of a special case. It's a shape that, how do you define this, right? How do you define this? Because it doesn't have a number of sides. We could define other shapes by their number of sides. So here's how we're going to define this. A circle is technically the set of all points. If you look this up outside of this class, you might see the locus of all points. You might see that fancy phrase. It just means like the collection of points. Here it's okay for us to just say a circle is the set of all points in a plane, I suppose that's fine, that are equidistant from a fixed point in the center. We'll call the center point, from a fixed center point. So if you ever thought about how do you define a circle? Because if I said how do you define a triangle, you could say, well, it's a shape that has, it's a closed picture that has three straight sides. That's what a triangle is, right? But a circle, how do you define that? Well, how we define it is we say you pick some point and some distance away from that point, and all the points that are equal in distance away from that center point, that whole collection is called the circle, the set of all the points. So this is, and of course we denote that with a solid curved line, just like this. The distance from the center to any point on the edge is called the radius. Oops, the radius. The distance from the center to any point in any direction on the edge is called the radius. We denote it by r. Okay. The diameter is the distance across the circle that passes through the center. Has to pass through the center. And denoted by d. Sorry, denoted. I'll put a comma there. Denoted by d, lowercase d there. So the distance across the circle from any point on the edge to any other point, but it has to pass through the center. I can't say the diameter is down here from this point to this point, right? It has to pass through the center like that. So this distance all the way across is called d for diameter. And you can clearly see that there's a relationship here between r and d, right? Diameter is twice the radius. Diameter is twice radius. D equals 2r. Okay, that's the relationship between diameter and radius there. All right, that's the definition of a circle and kind of its main components that we're going to talk about when we talk about finding area and circumference of the circle. We'll need these measurements. Well, in particular, we're going to need the radius, but can't really talk about radius without at least mentioning diameter, right? Very much related. Okay, now let's move into a discussion of polygons. So a polygon, here we go. A polygon is a closed shape, or I'll say a closed figure, that is determined by 3 or more straight line segments, 3 or more straight. So that's kind of the defining feature of a polygon, is that it should have straight sides. And technically, what are those sides? Well, in the using the vocabulary from section 6.1, those side lengths are little line segments, or rather those sides are little line segments, right? So a polygon is a closed figure, so it has to be closed, meaning you can't have something like this, right? Like that, that's like an open, it's not closed, right? As soon as I close it, now it's a polygon. It's a polygon. And we can classify polygons by side, by number of sides. So clearly a circle is not falling into this category. A circle is not a polygon. We can classify polygons by number of sides. Let's do a few. I'm not going to go too far, but we have 3 sides is a triangle. 4 sides, quadrilateral. 5 sides, pentagon. So once you hit 5, this is when they all start to end in agon, right? Like this is where they all start to have names that start to sound similar, right? 6 sides is a hexagon. 7 sides. We don't talk about these a lot, but it's called a heptalo. You know what? Yes, I believe that's what it's called. Actually, I haven't thought about it in a while, but yeah, it should be a heptagon. 8 sides, like stop signs, is an octagon. And 9 sides is a nonagon, and then decagon, and blah, 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 blah. Let's not go too much further. This is really, we're going to be mostly interested in triangles and quadrilaterals. There's a few other types of classifications we can talk about. 2 broad categories. So these are all just different types of polygons based off of number of sides. But then a broader definition, or 2 broader definitions of polygons, are convex polygons All right, here's the technical definition, and then I'll tell you what we're getting at here. Are polygons that have interior angles that measure less than 180 degrees. That means, so like all of these shapes that I listed here are convex polygons. Convex means that it's not concave. Like convex means the sides like point out. So here's like some convex quadrilateral. So, okay, you still might be wondering like, well, what does that really mean? It's easiest to contrast when you, or it's easiest to picture when you contrast it with the definition of concave. Concave polygons are polygons that have one or more interior angles with measure with measure greater than 180 degrees. What do I mean by that? So it has some angle interior to the shape. This is an interior angle right here that's greater than 180 degrees. See how it's concave? It's caved in. It's caved in. That's the way to remember it. At least one side is caved in, whereas a convex polygon has no sides caved in. You are going to be most familiar with convex polygons, triangles, quadrilaterals, pentagons. Most of what you've seen are convex. Now, it doesn't mean that these have to be convex, right? These things I've listed here, but most of what you've seen them drawn as, they are convex. In fact, this is a quadrilateral that is concave. It has four sides, but like I said, I'll say that again. Most of what you've seen have been convex polygons. Most of the calculations that you do in like high school geometry or wherever you might have learned this, and everything we're going to do is going to deal with convex polygons. Okay. Let's talk about angle measures for each of these type of polygons here, based off of number of sides. Let's talk about the sum of interior angles in a convex polygon. It actually works for concave too, but again, we're only going to be dealing with convex. The sum of interior angles for a polygon with n sides. Okay, so what do I mean by this? What am I getting at here, and what am I about to write? I'm about to show you a formula that tells you what the sum of the interior angles for a polygon are if it has n sides. What are some that you already know? What are some that you already know? A triangle, those angles should add to 180 degrees, right? The three interior angles here should add to 180 degrees. I'm putting different numbers of tick marks here, or angle measure marks, to show that these angles might be all different here, but they should always add to 180 degrees. And you might recall that for a quadrilateral, like maybe like something like this, these angles will sum to 360 degrees. Okay, so maybe, I've got some, well, I don't need to draw I don't really need to draw the, this kind of looks messy with when you get four angles. But the point is that the sum of all the angles, the interior angles, the angles inside, adds to 360. So what is it in general for a shape that has n sides? Well, it's pretty simple formula, n minus 2 times 180 degrees. So let's see this working for what's the smallest number of sides a polygon can have? 3, right? 3. So let's look at, for a triangle, 3 minus 2 times 180 degrees. That's 1 times 180. That's just 180. That's for triangles, so it works. Now, what about quadrilaterals that have 4 sides? 4 minus 2 times 180 degrees. It's going to be 2 times 180, right? 4 minus 2 is 2 times 180. And that's 360 degrees. What about a hexagon with 6 sides? What would that be? That's going to be 4 6 minus 2, 6 sides to a hexagon. Plug it into the formula. 6 minus 2 is 4 times 180 degrees. That would be 720 degrees. So what does this mean? If I have a nice hexagon, and let's just pretend like all the angles in it are equal, or let me build one where in fact all the angles in it are equal. So it's called a regular hexagon. Oof. And let's say that these are all equal. What would they have to be? So if I know that the total, by my formula here, the total sum of all these angles should be 720, and I know that all of these angles are equal for this little picture I've drawn for, they won't always be equal. I can draw some crazy hexagon that's all sorts of weird shapes, but in this one in particular, I've drawn so that all the angles are equal. What will the angle measure be? Well, I would have 720 degrees divided by 6 because there are 6 angles. And what does that give me? 120 degrees. So each one of these is 120 degrees. Here's a question. How about okay, let's say what is the interior angle measure on a stop sign? So I know a stop sign is an octagon. It's 8 sides. It's an octagon, right? That has 8 sides, right? That's what an octagon means. It has 8 sides. And since it's a stop sign, I know that all angles are equal because it's not some crazy weird shape where like all the side lengths are the same here and all of the angles are equal. So I know that. And how do I know that? Well, because I look at stop signs all the time, right? So I know that all angles are equal. But what is the sum of the angles inside? What is the sum of all of these angles? How many are there? There's 8, right? I don't know what each one is individually, but I know by my formula, then it should be that. N minus 2 times 180 degrees. Or N is 8 here. So I have 8 minus 2 times 180 degrees. So we can just pop that into the calculator. We'll get 1080. Just remembering our order of operations, subtract in the parentheses and then multiply. And now what do we do? I know that that's the sum of all the angles, interior angles. That's the sum of all the interior angles, and there are 8 of them. So now I'll divide that by 8 to find the angle measure of each one of these angles, and I'm getting 135 degrees. So if you went out and literally measured a stop sign, like brought out your protractor and went and measured the angle for one of these little angles, interior angles on it, you would get 135 degrees. Okay. Okay, real quick, let's talk about some special quadrilaterals. Let's talk about quadrilaterals for a bit. Actually, no, sorry. let's see, let's go in order here. Let's talk about triangles for a minute. In particular, similar triangles. So what do we know about triangles so far? We know the sum of their interior angles is 180. And let's talk about similar triangles because that tends to come up a lot. So we're not really going to worry about classifying triangles into like acute, obtuse, right, scalene, isosceles, equilateral, equiangular, all that good stuff. We're not going to do that. We're going to look at how can I use some triangles to solve problems. So let's talk about similar triangles. Two triangles are similar Two triangles are similar if the corresponding angles in the triangles are equal and the side lengths are proportional. Let me give you a quick example. So maybe I've got some triangle like this. Okay, let me say, I can redraw this. I'm going to draw this bigger so I can draw angle measures inside. So I've got some triangle maybe like this. And I've got an angle measure up here of 100 degrees, right here of 30 degrees, and then right here of 50 degrees. So I'm making sure that they add to 180 here. So that's 100, 30, and 50. And let's say I have side length here of 8, side length here of 6, and a side length here of 9. If I draw another triangle that's twice as big, roughly twice as big, right? I'm kind of limited by the size of my paper here. But if the three angles are the same, if that's 30 degrees, this is 100 degrees, and this is 50 degrees. Also, no, I'm not putting like multiple angle lines here because I'm actually like writing the measure of the angle here. So I don't need to put extra angle lines because I'm being specific about what the measure of the angle actually is. So if I want to show you two triangles that are similar to each other, what that means is I've basically scaled the triangle up and all of the angles have maintained the same size, and the side length should be proportional. So if I say this is twice as big, that side length should be 16, this one should be 12, and this one should be 18. The side length should be proportional. And that means you can build proportions out of these triangles too, to solve for like missing sides. So we're going to do an example. But the point is that if you know two triangles have the same angle measures, then the sides should be proportional. That means, for instance, like if I didn't tell you this side, I said it was X, how do you solve for X? You set up a proportion. You say, well, let's see, X is to 18, X over 18 should be equal to the corresponding sides over here. What side corresponds to X? 6. What side corresponds to 18? 9. So then I could solve this proportion by cross multiplying 9x and then whatever 18 times 6 is, cross multiplying here. And then dividing both sides by 9, and I would get 12, which of course I already told you it was 12, right? And maybe it's even easy to tell. If you can tell that this triangle has just been doubled, then you don't really need to walk through all of this proportion math here. if you already know it's been doubled, you can tell the side is 12 without having to do the proportion. But that's a very useful technique. So let's see how we can use that in a real life problem. Okay, a man who is 6 feet tall, is standing 20 feet from the base of a tree. Okay, the sun shines on the tree and creates a 30-foot shadow. 30-foot long shadow. How tall is the tree? And they give you a picture to go along with this too, so maybe that'll help set this up. So here's the tree. So this is like the tree here. Okay, that's my tree. Okay, and let's say maybe that's its height there. And it's casting a shadow. The sun up here is casting a shadow. Right. And the guy is, oh, in the shadow, draw the shadow first, is 30 feet long. And then there's a little 6 foot tall guy standing here. 6 feet tall. And he's standing, how many feet from the base? 20 feet. So from here to here is 20 feet from the base of the tree. We want to know how long is this side? How tall is the tree? How tall is the tree? Let me redraw this without all the mess here. So I've got a triangle. I've got an unknown side here, x, and I've got a base 30. Then I have a smaller triangle, little guy, side 6 length there, height of 6. And how long is this base? How long is this piece here? All right, all the way across is 30. This is 20. Of course, this must be 10. Right. Okay. So all the way across is 30. This little triangle was built inside of here, right? And this distance from the tree to the guy was 20 feet. So the remaining distance must be 10. So I pulled 2 triangles out of this. There's the bigger one and then the one inside. And they must be similar. They are similar. Why? Because they have the same angles. First of all, they're both right triangles, right? And the angle of elevation of the sun is going to be the same. Like whatever this angle is going to be the same there, right? Because it's the same sun for both the tree and the human, right? The sun is coming at the same angle. And of course, that means that the remaining angle would have to be the same as well. So they are similar. And that means I can set up a proportion to solve for the height of the tree. I'm going to solve for the height of the tree with very basic math, right? Very basic math without ever having to get up and climb the tree or anything like that. So how do we set up the proportion? We say x is to 30 as 6 is to 10. And you may say, are there other ways to set up the proportion? Yes. You could also set it up as x is to 6 as 30 is to 10. To me, it makes more sense, though. This setup here makes more sense. But of course, they end up being the same thing. So we end up with 10x is equal to 180. And x is equal to 18. So maybe you already saw where that was going, just based off of the fact that you can tell that this triangle has been scaled up by 3. You won't always be able to tell what it's scaled up by. Oops. You won't always be able to tell what it's scaled up by, but in this case you can see this triangle is 3 times as large as this one, because look at this side length, 10 to 30. That's multiplied by 3. So 6 to blank, well, it must be 18, which is exactly what we got. So the tree is 18 feet tall. Whoops, whoops, whoops. You could do this in real life. You could go, you know, you got to know your height. You could go measure the length of your shadow at some point in the day, and then go find a tree or some tall object and measure the length of its shadow, and then set up a proportion to solve for the height of the building or tree or whatever the object is that you're measuring. The only thing is you got to make sure you do the 2 shadow measurements like at the same time of day, because of course the sun moves, right? At the angle of the you know, we cast longer shadows in the evening because the sun is lower, right? So the sun is moving, so you got to make sure you do the calculation or the measurements at the same time of day. All right. Now let's talk about quadrilaterals. Quadrilaterals. Let's just classify some.